estimating percentages. And that's fantastic. We're going to revisit that today. I got, like I said, this little activity I built up for today involves spinning coins, taking some tests among us, and then I'm going to spread you guys out throughout the building to do this, I think, because we're going to need some more room than we have. But I want a real quick recap. Pull this down here. I want a real quick recap why that's not enough. Percentages, fantastic, love them. But it's not enough. Let me slide this over to the side here. We'll come back to it. So that is what I loosely term estimating a population proportion. So estimating little p using p hat. This is great. This is a question for everybody. Which one are we going to get from our data? P hat. P hat we're getting from our data. Which one are we never going to know? Never going to know that one. But at a set level of confidence, here's what we want to happen. At a set level of confidence, that's what we want to happen. Oh, it is. I'm sorry, Zoe. It's so funny because every time I start this class, sometimes I use E, sometimes I use MOE. Yep. Thank you for catching me on that. Margin of error, margin of error. If I inadvertently do it on assessments, just realize that a big E just means margin of error. So, but I'll try to be consistent. Now, this is a 95% hope. We never know for sure. Screen share again. We never know for sure where the center is. So we're going to be off center more often than not, but that's what the margin of error corrects for. So that 95% of the time we actually catch it. And this is fantastic. If we want things like the percentage of times the penny falls heads up, the percentage of respondents that are in favor of Congress, the percentage of Americans that are uninsured, or something like that. It's all about percentages, all about little p. We also, however, need a second tool which covers the other kinds of data, the continuous data, or data that we're averaging, discrete data that we're averaging. And this is what we started on last Thursday. Not estimating p, but estimating, do you remember? So go ahead and be brave. Mu. Nice and loud. That was it. It's mu. Yes. So using x bar, we're going to estimate the population average using x bar. Estimating the population average using x bar. Yes. And it looks the same. It looks the same as the proportions, at least in setup. You're going to have a mu value that is out there somewhere in the world, and you don't know its value. It's on a distribution, and so is your sample data. Your sample data is also on a distribution. And the central limit theorem tells us they line up, and we're happy about that. The problem is, your x bar, don't write this down, is not going to equal mu. We learned this back in 243. X bar doesn't equal mu. X double bar does, if you remember that. Remember what X double bar was. If you don't, that's totally fine, Jared, so we're going to take that away. You say it doesn't equal mu. So how do we correct that it doesn't equal mu? We attach the margin of error to it. And we say that 95% of the time, whoops, plus. Yeah, I should probably write then talk. 95% of the time, the value of x bar plus or minus its margin of error is going to capture the value of mu somewhere within that interval. In other words, the fishy. Should I keep talking about the fishy or something? Let the fishy go. Is the fishy okay? What is the fishy? P, or in this case, good, it's the parameter. Very nice. It's either P or it's mu. So you've got these fish tanks, if you will, set up where the far value is your sample statistic minus the margin of error. The upper value is your sample statistic plus the margin of error. And your fish swims somewhere between. Somewhere between. All you know is it's at least this number and at most that number with 95% confidence. You don't know exactly where it is, but with 95% confidence, you know it's between those two values. FYI, your second project really dives into what 95% confidence truly means in a statistically historical kind of way. So over here, same thing. Your fishy here is p hat fishy. Excuse me, your p fishy, not your p hat fishy, your p fishy. Over here, over here is going to be x bar minus the margin of error, x bar plus the margin of error. And you're going to have which fishy over here?
Mu fishy.
It's going to be your, should we make them look different? Give them like a fancy tail, maybe. That's your mu fishy. He's in there somewhere, Susie.
And this might sound stupid.
No, I doubt it. Go ahead.
Okay, so the only difference between the two is P is for the whole population and mu is the average, no?
They're both for the whole population. P and mu are both population parameters. Bob, go.
I thought it was samples.
No, the samples are here and here. It's what you're trying to estimate from the population. Is it a percentage within the population, or is it an average within the population? You know, that's the difference. The difference, it's usually a data type. It's a data type. Is it discrete data, or is it continuous data? That's the usual. So are you talking about counting and dividing, or weighing, or measuring, or temperaturing? What's the verb of temperature? Taking a temperature. There we go. Make it a phrase. So really, the difference is not population versus sample. Both have a population. Great question, by the way. Both have a population parameter, and both have a sample statistic. The question is, how do you know which one to do? And the answer is context. You have to be able to look at the problems. So when we did Del Taco half-pound bean and cheese burritos, what were we trying to find? The average weight of a Del Taco half-pound bean and cheese burrito. So therefore, we had to go this route because we weren't looking at what percentage you're over a half a pound. We were looking at how much do they actually weigh. So it's all contextual, which is what most of this class is context. What am I trying to measure? Is it a percentage of something, or is it the average of something? And it will always be back and forth, I promise you, for the next 8 weeks. It's always back and forth between those two ideas, whether it's a percentage or an average. Is that fair? Good. Other questions? That was a fantastic question. Because that's a big clear up to talk about right off the bat, to make sure we know. These essentially are doing the same thing on two different contextual ideas. So thank you for that question. Please, Ben.
I want to make sure that I remember what you just said.
Sure.
I think I forgot.
Well, that's why we have it on video archive.
Both have a population parameter and both have a sample. Okay.
Population parameters,
Yep.
sample statistics.
Okay.
And these are, the reason we're talking about these and not like a median or a quartile or a range is because these unbiasedly estimate these, which means, on average, they land next to the parameters they're supposed to land next to.
Okay.
So, go ahead, does that make sense?
No, yeah.
Excellent. Ben, did you have a question back there?
Oh, no.
Okay, Chris, go ahead.
They're both inferential?
Everything is going to be inferential. The statistics themselves are not, but as soon as we slap a margin of error, they become inferential.
Okay.
Because we say, I am 95% confident that. That means we're uncertain, but we're making a hypothesis based on that sample statistic. Everybody hear that question? That was fantastic. This is all inferential. The statistic itself is not. You draw a sample, and you report back the sample center, p hat or x bar. That's descriptive. It's describing the sample. But as soon as you make the claim, I am 95% confident that the average weight of a Del Taco half-pound bean and cheese burrito, not the 30 that I measured, but all of them, that becomes inferential. Does that make sense? Not to over-answer your question, it's a great question. That's all I have, but Bob, go ahead.
So you're going to use one of them when you're using the discrete data most of the time, and the other one when you're using continuous data.
Yes, although,
I know there's going to be exceptions.
no, and it's minor exceptions. I bring it up only because the next one we're going to do is actually an exception. Only because you're going to be counting the number of times you get something right, and then we're going to look at the average number of times you get it right. Not the average percentage the time that you get it right, the average number. So basically, yes, a good way of looking at it most of the time is discrete versus continuous. But there can be some discrete cases that sneak in here. But just think, that's why context, percentage or average. Look for the actual bigger word. That's 100% confident. I can be that 100% confident that this is always doing percentages and this is always doing averages. Usually it's discrete and continuous, although you can average discrete data. You can't percentage continuous data, but you can, well, you probably find an example where you can too. I'm sure you can if you look hard enough. But the big, if you're looking for, and I love what Bob's doing, he's compartmentalizing, which we should all be doing. How to know what to do here versus what to do here. So in other words, how to know on your TI, this one here, this shortcut was called 1prop z int, right? This guy here is 1prop z int. And this guy here, and we'll take a break here in a minute and come back to why the T is there again. I want to make sure we take about 5 minutes to do a history lesson on that. This guy here is called T interval. Interval. And I want to make sure when we come back from our 5 that we have a brief history lesson as to make sure we know why one's C and one is T. Brief history lesson, and not to be memorized, just to be explored and kind of like, okay, it has something to do with that beer Guinness. And we'll real quick revisit back into that. And then we'll send you loose on an activity where we collect some data and then analyze it using both. Because we'll have discrete data, we can do it both ways. Jamie, go ahead.
Before we all go.
Yes.
There is a, white boxy Chevy, car that has slid down into the
Ooh,
driving
goose.
path,
Does anybody drive a white boxy Chevy car?
just in case. It's
Okay.
like right out.
What we'll do is I'll go to
on the
each classroom and tell them to a white boxy Chevy car, not a truck.
Car.
It's a car. All right, let me turn the camera off now that all of YouTube knows that.